Well, I think Mark Robinson had it right last night when he said that the King Crater region is so rich in detail that one could easily give 10, 12-minute presentations on the subject. So I'm actually going to concentrate on the mapping aspect of this, and also I've added a subtitle here highlighting new insights into melt pond dynamics that we think we're learning from our study of the melt pond region. King Crater is located on the lunar far side. It's just north of the equator. It's an example of a young Copernican to late Eratosthenean age complex crater system, and is approximately 77 kilometers in diameter. It, we think, had an oblique impact to create the asymmetry that we see here, evidenced by the peculiar claw-shaped central peak, the distribution of melt, notably in the north-northwest region, where it, accumulated here in this pond, which will be the object of our affection for the rest of the presentation. And a few additional features. It's compositionally complex, as evidenced by Clementine data. It's a Tier 1 constellation region of interest because the large melt pond represents an opportunity to study high volumes of once molten norite and orthosite material. One moment. The rectangle outlined in yellow will be the extent of the WAC geologic map, and the smaller red rectangle will be the NAC geologic map, which we have centered on the melt pond. This is the WAC geologic map. We use Adobe Photoshop to create the maps, using a WAC mosaic as a base map, and a range of incidence angles from the WAC images. And also the WAC DTM is used to indicate the locations of contacts and help out with the mapping process. The ejecta blanket has been separated into distal and proximal units. The crater floor material, however, is undifferentiated. There is a lot of interesting features in the crater floor, a lot of anomalous features in the crater floor, especially at the NAC level. We leave that as undifferentiated at the WAC level. The central peak is grouped with its own slump material. Viscoid forms are noted in the melt pond, but they're not differentiated at the WAC scale. Once again, this asymmetry is something that you can see running along the axis of the cross-section here. Note also the breach in the crater wall, which is very evident in the cross-section. This is the NAC geologic map, representing the pond itself is something like 400 square kilometers of surface area, and it is occupying this pre-King Altuzzi crater. Now, if we assume the crater to be a simple bowl-shaped crater, we can come up with an estimate for the thickness of the melt at the deepest point of approximately 175 meters. As you'll see in just a moment, we don't think that it is a simple bowl shape. We think that it's occupied by significant amounts of ejecta from the King impact event. But notice in the NAC geologic map, we have differentiated some viscoid forms that represent late stage arrival of melt material to the pond. Most of the material came from the southwest and entered the pond from these directions, also some from up here. The WAC DTM contours can be used to establish that, yes, indeed, the surface of the pond is horizontal and relatively flat, at least at the 20-meter contour interval. And notice that that is the case primarily for the eastern two-thirds of the pond surface area. The western third is a higher elevation province, and again, because of the late stage arrival of viscoid melt, whereas the eastern two-thirds are probably representing an equipotential surface of very low viscosity material that arrived early. Robert Wagner and Drew Enns and Nick DiCarlo of Arizona State University have put in countless hours on the NAC mosaic to identify a large number of features within the pond, and I'll illustrate some of those here. I've broken them down into three categories. The flow features are represented here in orange, and you can see that, yes, indeed, they dominate the western third of this area. and are associated with these late-stage arrivals. The eastern two-thirds, well, the positive relief features we see distributed pretty much uniformly with the exception of this one large feature across this melt pine. And again, this is probably representative of ejected deposits, although they are covered with a veneer of melt material, melt-rich material. The negative relief features will be the focus of the rest of this talk. These are highlighted in lavender, and you see them throughout the eastern two-thirds again in this equipotentially stable region of the pond. Notice very quickly, if you will, their distribution, that they do not, they're not uniformly distributed. There are voids, if you will, between occurrences of these features. Let's take a look at what some of these features look like. There's actually two different kinds. There are sharp lineations, which one might visualize as being the result of extension, and they grade into undisturbed topography pretty seamlessly. There are also occurrences of these lineations around the perimeters of some of the positive relief features that look almost like moats, which is a very puzzling circumstance. But we also have some of these features that are simply too wide to be the result of extension. They have to be the result of some kind of collapse. And particularly in the case of this bridge, if there was an extension involved here, you wouldn't have this arch occurring. So this is the result of collapse. So you had to have some kind of drainage and subsequent collapse into the void space that resulted from the drainage. Now let's take a look once again at this map with the negative relief features, the linear ones highlighted, but also with a layer of the NAC DTM. We're trying to increase the coverage of this DTM across the entire pond surface, but for now we have this one. And below the 20-meter contour level, now we see some variability. We see moderate to high correlation. And notice that the blue is low, red is high. Moderate to high correlation along the perimeters of these down-warped zones. Now, these are not stair-stepped in cross-section. These are very smoothly down-warped zones. This is the most prominent one, but you see others here, here, here. And they seem to occupy the interiors of these negative relief feature scarce zones that I was mentioning a moment ago. Now, what is causing this? Well, this is an explanation that we're proposing. If we imagine that the floor of Altusi crater was littered with debris from the King impact before the arrival of this low viscosity melt, and so it had an irregular surface, which is represented here in cross-section, of course, as having, once that equipotential surface is achieved, varying thicknesses or depths to the melt. Well then, of course, as the melt begins to cool and it forms a crust on its upper surface, these are the zones where you're going to have the greatest amount of vertical contraction from cooling, and then the simple down warping of these zones is going to result in separation cracks at the places between these zones of highest subsidence. So that's a fairly consistent explanation for why we're seeing what we're seeing, where we're seeing it. But it doesn't, of course, explain the collapse features, and we're still scratching our heads about that a little bit. Obviously, they happened. Somehow we had some kind of late-stage drainage of the melt that resulted in the occurrence of these peculiar void spaces. Was it a combination of contraction and drainage into some kind of porous media, drainage into fractured bedrock beneath Altusi crater in the megaregolith? This is unlikely, but the ejecta deposits within the crater are, conceivably highly porous. Was there any seismic energy involved that could have helped to cause these late-stage adjustments, perhaps from some of the secondaries associated with King? Or is it simply the natural response to the cooling of a large volume of melt material? These are things that we're trying to figure out. So in summary, the King crater region has been mapped at WAC and NAC scales. This downwarping sagging of select regions within eastern two-thirds of Altusi Pond correlate with intersag separation cracks moderately to highly well. The collapse features show evidence for gravity-driven infiltration of some kind or another of late-stage molten material. And we wonder about the connectivity of the void-based plumbing network, because it may be suitable for subsurface habitation and exploration in the future if we ever get to this place. Thank you.
Okay, James has left himself plenty of time for attack through questions. So, questions? We were all on the decaf again, were we? Let's start with David and then Paul.
Okay, if your model of cracking is right, does that require specific thickness of the melt?
I'm sorry, specific what?
Thickness of the melt. Earlier in the talk you had said that it wasn't as thick as you estimated deposit, but you didn't actually, I think, say how thick the melt ranged from.
Yeah, that's a calculation that I have on my list of things to do that I want to make and have yet to make, is based on our assumed composition of norite and orthosite. What exactly are the volumetric changes that thicknesses, varying thicknesses we would expect to subside? That would help answer a lot, I agree. So that's something we're going to do.
This is fascinating stuff, and
this is Paul Warren, by the way.
It's fascinating stuff. I'm looking forward to more of this when other craters are scrutinized like this, and you'll do more with King. Regarding the drainage hypothesis into the porous ejecta deposit, I would just comment that it might not be purely a mechanical process. There may be some thermal erosional aspect to it, where I imagine you've considered this, that you could just reach a threshold where you've concentrated melt in some locale, and at some point it just kind of opens up a channel. So that would be an interesting process in itself, if it ever.
Yeah, I agree, and I'm trying to visualize what it is exactly that's going to do that. Open up a channel at some late stage after the crust has achieved itself. And a lot of different scenarios. But,
yeah, I was particularly intrigued by the fact that you said the seismic energy from secondary impacts could have promoted that. I thought the secondaries had already happened by then. So
yeah, there's a timing problem with that, of course.
Yeah, and don't forget that the moon itself does give you rather large moonquakes. The shallow moonquakes can be body wave magnitude up to 5+.
Indeed.
So the moon could be at that time could have been shaken quite nicely. So
indeed.
So any other questions? We still have time. I told you left yourself open. I mean,
I actually cut about 10 slides because I was worried about going over.
Oh well, that's impressive, but I wouldn't do it again. Any more questions? Go once. Oh, you're getting off lightly. They're a kind audience. Oh, there's one in the back. One in the back.
Do you have any idea of how hot the melt material was from its fluidity and the fact that it spread out so flat?
I wish I did. I do have other images, NAC images, of the melt occurrences within the terraces of King Crater walls that show a cascading effect to the behavior of this melt. In other words, there are plenty of indications to show that it was extremely low viscosity stuff.
Which indicates that it may have been very hot.
Probably.
If it was very, very hot and it ran into other material, is there a chance that it could crust over on the top and then melt stuff on the bottom and collapse?
I don't see why not. I mean, it's certainly going to influence anything that it flows over.
Is there any chance it would run into something which would be even lower melting than it is and chew into it?
Yeah. There are all kinds of mysteries associated with this melt that we're seeing at the NAC scale all over the surface of the moon.
All right, Carly jumped up there and pleaded. She's going to give us another poem, I think.
Well, I'm just intrigued by the comment that you raised, Clive, that's related to this. And I was thinking, well, remember all the wonderful seismograms from the lunar seismic experiment and how things ring for a long time after small events. Well, this is a big event, so it's going to be ringing. And I'm thinking that must affect how things flow and the whole sequence of emplacement, and perhaps even the formation of some of your void areas.
And if it goes on
Really
for 30 minutes, then that certainly could may